Can you see my screen?
Yes, it's here.
Okay, let's begin. Okay, I will start with the problem statement. What do we mean by image enhancement? This is where everyone begins. We have a not high resolution image, a little bit blurry image, and we want to enhance it. This is what people think that we will be getting. Before we move on, here's the expectation that most of the people guess that they would be getting. Why? From TV shows. The classical zoom enhance. As if satellite can turn 10-meter pixel into crystal clear license plate, for example. So we have to lower our expectation here because the enhancement of image resolution is not as much as you think. At max, it could be giving you ×2. Okay, why does resolution matter? Resolution isn't just about making an image look pretty. Details directly affect what you can detect, how well you can classify features, and the accuracy of any map you produce. The image is fuzzy, so your analysis will be also fuzzy. Okay, in remote sensing, we have a trade-off between these three aspects: spatial, spectral, and temporal resolution, because no sensor can maximize all three at once. Pushing for finer spatial detail usually reduces spectral richness or revisit speed. Adding more spectral band typically lower spatial detail or slow coverage. Okay, so why do we need enhancement? Most tasks need two things at once: sharp spatial detail and strong spectral information. But multispectral images give you the spectrum without the fine details, and panchromatic images gives you detail without the spectrum. That makes small object hard to detect and classification less reliable. And getting truly high resolution multispectral data is expensive. So the real problem is simple. We want the sharpness of panchromatic imagery and the spectral richness of multispectral imagery in one product. I will start by talking about some of the old approach that is still being used until now, and we will move on to the newer approach, which is using deep learning. One simple approach, it's not really enhancing, which is the resampling method, like the nearest neighbor bilinear or bicubic, where the earliest attempt at enhancing resolution. But as I said, let's be honest, they don't actually enhance anything. They stretch the image and guess the missing value. You end up with a larger image, not a smarter one, and definitely not a more detailed one. Okay, just a second. Like, for example, this one, as you can see, it's a little bit pixelated. So if I resample the image, all it does, it makes it smoother. So not really enhancing as much. Before talking about the other traditional method, I want everyone to understand something. We often work with two very different kinds of imagery, and each one is built for a specific purpose. A panchromatic image is collected in one broad wavelength range, so it captures a strong signal and produces very sharp spatial detail. It looks like black and white, the one that you can see on the left. Okay, the key advantage for the panchromatic is the clarity that it gives. Small feature, edges stand out in this image. On the other hand, we have the multispectral image. is collected in several narrower wavelength band. This gives us real color information and let us understand material, like for example, vegetation health, water condition, and other surface characteristics. The trade-off is that multispectral images usually come with lower spatial detail because energy is split across multiple bands. So in general, panchromatic images are about where things are and how clearly we can see them, while multispectral images are about what things are based on their spectral signature. So both are valuable, but for completely different reasons. Okay, the other model that I'll be talking about is called pansharpening. So in this slide, I'm going to show a classical pansharpening. On the top left, you can see the original color of the image, which has good color, but relatively low clarity. It's 2040 centimeter resolution. And on the top right is the panchromatic image. As you can see, it's a grayscale, but it has much finer detail, 60 centimeter resolution. By fusing the color information for the first image with the spatial detail from the panchromatic image, we get the bottom result, which is a pan-sharpened color image at 60 centimeter resolution that keeps the color but gain much sharper detail. So we get detail from the panchromatic with the high resolution, and we fuse it with the original image, which has all the other band but have lower resolution. We have different methods. I will be stating the title. I will not go into detail. Okay, we have different methods, like as you can see, Provi, ESRI pansharpening, GAM Schmedet, IHS, and the simple pansharpening. Each has its strengths and weaknesses, and when is the best use case to use it. Like for example, where can you find this tool to use it? One of the example is ArcGIS Pro. You can find that tool. All you have to do is give it a input raster, and it will store it somewhere, the output, after applying the pansharpening. And you give the panchromatic image, the one that have more detail, and you select the method that will be used. And as you can see above, we have 3 channels. You have to define if your image as you said, it's a multispectral image. So it have multiple bands. You have to select which each band is which in the image. And finally, you can give weight for each one of the bands that you have. Okay. Before we jump into deep learning, super resolution, it's worth calling out why we need anything beyond traditional pansharpening in the first place. Classical method can generate true new detail. They only reshape contrast from the panchromatic band, so the extra sharpness is mostly cosmetic. They also introduce spectral error, especially in vegetation, water, and built-up area, that make them risky for any analysis that depend on accurate reflectives. Bottom line, traditional pansharpening is great for pretty imagery, but not trustworthy for quantitative. That's exactly the gap deep learning super resolution is designed to fill. Okay, before we begin, I will be talking about different types of resolution. When we say resolution, it's not just one thing. Most of people think about spatial resolution, like how many pixels are in the image, or the pixel in the image, how much area it covers. So we have 4 different types of resolution. We have spatial resolution, the one that everyone knows is the pixel size on the ground. For example, if I say it's a 10-meter image, that means each pixel covers a 10 by 10 meter area. So anything smaller than that gets blended into the same pixel. So if we have multiple feature within the 10 meter, if my image is 10 meter, all of these things will be blended into that pixel. The other type of resolution is the spectral resolution, is how many wavelength band we have. For example, RGB give us three band, while a multispectral sensor might give us 8 narrower ones. The other resolution that we have, the third one, is the radiometric resolution. Is the bit depth. So, for example, an 8-bit image gives us a 2056 possible value per pixel. So each pixel have this number of value that it can hold. Another example, a 16-bit will give us much higher, I think 65,000 something. That extra range help detect subtle brightness changes. And the final resolution that we have is the temporal resolution, is how often we get a new image. For example, a sensor with a 5-day revisit give you a fresh look at the same place every 5 days. Okay, and the enhancement I'm gonna be showing you today focus on the two that matter most, which is the spatial and spectral resolution. Okay, just a second. So, okay, you still can see my screen, right? If you can, write it in the chat, please. Okay, AI has been transforming remote sensing uh, across the board. We've already seen it take over tasks like bland cover classification, semantic segmentation, object detection, and change detection. These models aren't just doing math trick. They are learning pattern directly from real imagery. and that same shift sets the stage for for our focus here. Deep learning for super resolution, enhancing the resolution of the image. Instead of relying on traditional contrast-based sharpening, this model actually learn texture, shape, and spectral relationships. That means they can reconstruct fine-scale detail in a way classical pansharpening simply can match. Okay, this is the moment the field moves from visual enhancement to genuinely smart resolution. Before we begin in the specific example, I will give you an overview about the AI tools that can be used out of the box without coding in ArcGIS. So ArcGIS supports both codeless and code-first deep learning workflow. Okay, so you can write code and you can just use that tool provided within ArcGIS Pro to do your AI task or deep learning task. Most of the people, when we talk about doing something related to deep learning, the first step is configuring the environment. As you can see, we have different library when we want to do deep learning, like the one that you see on the screen. And most of the time, this takes time. Configure all the library to match, to have version that doesn't make conflicts. So this is a little bit this take a little bit of time. In ArcGIS, instead of downloading each one and matching it, you can just simply use something called deep learning framework. Deep learning framework combines all of these library that is needed and integrated within ArcGIS Pro. So first, you get all of the library already configured. So if you're doing coding, you can directly start working. And the other one, the tools within ArcGIS Pro that are powered by this library, like the one that we will be using for the super resolution, and even other tasks in deep learning are already enabled whenever you download this one. This library can be found publicly. You can download it and use it. All you have to do is search for deep learning frameworks, and you search for the GitHub repo, and you can find the library that matches, if you have ArcGIS, the version that you have. When we say deep learning, that's mean we must have like a good infrastructure, a good computer to do the deep learning, do the training. So in case you don't have, there's alternative. If you have, let's say, a specific task that require, like, let's say 1 month, 2 months, and you don't want to buy or invest in a powerful computer that is a little bit expensive. So your alternative is using the cloud services, where there are multiple cloud services. The simplest one is the Google Colab. It just gives you a notebook to write your code there, and you can do deep learning. You have also Google Cloud, the platform. You have Azure notebooks. So you have different options. You can choose the best, the one that best suits you. Okay. I'm not going to go into detail in deep learning. I want you to consider it as a black box. There's a lot of detail, but for the sake of the 1 hour today, I will consider just as a black box that you give it an input and it gives an output. Some of the application of deep learning, just to give you some additional context, is classification, for example, assigning a label to an entire image, like the first example that you can see. In general, like classifying if this image is a dog or a cat. More specific to GIS, let's say if we have the building footprint across a specific area and we want to see if a building is damaged or not. So we can do classification. Each building is classified either damaged or not, and we have many other applications. The other one is the segmentation, which classify each pixel in an image into a different category. For example, identifying road, it could be identifying road, buildings, vegetation. We have two types. I might talk in the next slide about it. The third application is the object detection, which identify and locate object in an image with a bounding box. So you give it an image, it detects an object, and it gives you a bounding box. The segmentation, you give it an image, it generates another image classifying these objects, as you can see. Like, for example, for object detection, could be used for detecting building, vehicle, even trees, if you want to count trees in an image, in a satellite image. And like common feature extraction, other stuff. And lastly, we have the super resolution, that was the one that we're interested in today. I will give an example later, which is you give a low resolution image and it enhances by a little bit. So don't really count that I will be having a 10 meter and it will give me a 1 meter image. So it enhances it by a little bit. Even this image that I did put here is a little bit of an exaggerated image. Okay, before diving deeper into deep learning, let's talk about how the model is trained. How does this model, how does this black box that I have, I give it an image and generate a more sharper one. How does it work? Before uh, before having this smart model, we have to train it. We have two ways to train it. One way is training it from scratch. I have a model which is empty, it doesn't know anything. I train it from scratch. The the downside of this is we need a large data set. What do I mean by train a model? Since the task of the model is generating sharper image, for example, I give it a high resolution image and a low resolution image, and I tell the model, you see the image here, this is the high resolution. Sorry, this is the low resolution. It should be like this one. So the model, okay, training it from scratch is needs a large data set. It's time consuming. It takes a lot of time since you're training it from scratch. It doesn't know anything and you're training it. Yeah, since it needs a lot of time and a lot of data, it's computationally expensive also. So we have this approach and we have the other approach, which is we already have a model and we can adapt it to our situation. Like a model that has been trained on detecting some type of building in another country, you can adapt it to detect building in your country. Since the building, and let's say building in USA and building in Lebanon, the building in USA is still the same structure as building in Lebanon. If you look at it, it's like a square, but the details in the image is not the same. So the model might work, but not as accurate on the US image. So you have to fine tune it. Let me simplify it. Like you have someone that knows how to detect this building, and I'm showing it some samples about the buildings in Lebanon. So the benefit of this is no need to this big data set to teach the model. All you need is a smaller data set to adapt this model to your situation. Same thing goes for the image enhancement. If the model was trained on image that is not in your country, it could be adapted. So the performance of the model could be better. Simplest example, if you want to understand the idea, here we have a model that detects cats. Instead of training another model from scratch, we can get this model, fine-tune it, train it a little bit, and it could detect tigers. What do I mean? We have the model, we get some images of tigers, and we show it to the model, so the model know how to differentiate between them. Okay, this slide I will go quickly over it. Whenever we train, we have to divide our data into three parts. One to train the model, the other one for validating each time we train the model, and the final one to test the model to get the actual accuracy and precision of this model. Okay. Sometimes you don't have much imagery. You can use data augmentation to generate more, and even not only to generate more images. In our case here, we will be the quick example that I will be showing is using one of the image manipulation method to add some blur, which is simulate the low resolution image. Okay, within ArcGIS Pro, you have all of these tools. No need to write any line of code. You can just put the configuration and get the model and the result. Like train the model, fine-tune the model, create the training data, and finally testing the model. And you have in the documentation, each one of the parameters explained what it is and how to use it. Okay, why is deep learning essential for GIS? Deep learning automate complex tasks in GIS, like, for example, land cover classification, building footprint extraction, and object detection from imagery. It's essential for handling large-scale dataset that will be impossible to process manually. The example here show real use cases detecting building, road, trees, and utility lines, and local parser from satellite or even drone imagery. So this leads to a faster, more accurate mapping, especially in disaster response, urban planning, and environmental monitoring. So these are different examples that could be used for. Okay. Another task that we are interested in today within deep learning is enhancing images resolution. In this example, you can see what that means in practice. On the left is the original low resolution imagery where everything is blocky and it's hard to tell what's what. On the right is the output from an AI super resolution model trained on high quality image. It takes that same blurry input and predict a sharper, more detailed version. So road, building, short line, and then use pattern become much clearer without us having to acquire new high resolution. As I said, this is an exaggerated image. It doesn't do exactly that, just a little bit of enhancement. As any as any other task, we have a workflow that we must follow. The three main parts are the data preparation, train model, and inferencing, and the other one is the after getting the result. Okay, so let's begin with the first step, the data preparation. We prepare input imagery and labels, which is digitized, like for example, digitized building footprint, and then using one function, since the model doesn't take the entire image. If we have a satellite image, the model doesn't take the entire image at once. So we have to cut it. We will see how in a bit. So the first step is the preparation of the data. So we give this cutting tool the image, the label, and it exports the training data to be ready for the next step, which is training the model. In training the model, like for example, we have multiple models. Let me show you some of the examples of the models that are directly integrated into the platform that you can use. Okay, if you search for ArcGIS Python API, these are some ready-to-use models that you can directly plug and play. So you can find it. You can find some trained model, and you can use this model from scratch, which is here. We are talking about 2D object. We have different tasks: object detection, pixel classification, tracking. So you have this model, each model, and the architecture of the model, some description about the model. And even, let's say, if you want to use a trained model, there's a lot of trained models that you can use. Instead of training from scratch, you can find the models here. If you search for Living Atlas, ArcGIS Living Atlas, you go to browse, you can find some data here. If you want to search also for a deep learning model, you can see a lot of deep learning models. Like for example, let's see some of them. Building footprint extraction, segment anything, tree detection, point cloud classification. So you have different models. You can use it as it is, or you can download it and fine-tune it a little bit to make it work in your study area. Okay. So the first one, as I told you, is the data preparation, then training the model that we saw. And finally, after training the model, we can apply the model on new area to detect features like trees, cars, roads, or even as we are working today to enhance image resolution. One more thing about this model, if you want to read more about the super resolution model, you can see it here. Okay, here, how super resolution works. And the other one is the SRG super resolution. You can read about each one. You can even try them on your images. Okay, after finishing the inferencing, applying the model of the new area to detect feature, we can derive insight. Convert the detection result into feature classes for further spatial analysis. Like for example, for one small example, I have an image. I want to count the trees in the image, so I can use the model to detect these trees. And whenever I finish, I can then use this result, like for example, get the health of each one of these trees. Okay, and this is the derived insight part after finishing the deep learning part. And of course, you can finally, whenever you finish, share the result, whether it's static like PDFs uh, or images, or printed images, or you can share it as web application within the ArcGIS platform. This is much easier. Whenever you finish, just a couple of clicks, you can share it, put it in a map, web map, interactive map, and encapsulate it within a application, whether it's a dashboard or any other type of application that we have on the ArcGIS platform, like for example, story map, experience builder, instant app. Each one have its specifics. These are the tools that you mainly using in the three main steps, which is the export training data that I talked about, and the trained deep learning model, and finally the detection of the inferencing part, which is depending on the task that you're doing. It could be detecting object or classifying pixel. Okay, this is the interface of the tool. As I said, no need for code. You give it the image. You define where you want to export or training data. Remember, this is the part where we said we have an image, we want to divide it into chips, like smaller part, since the model doesn't take the entire image. So this is the tool that does that. If we're doing some task like detection something, we have to label the data. So the feature class that holds the label should be put here. But since we are doing super resolution, I didn't need to put it. And finally, we have to define the chips that we want. How do we define what's the number? It's when we say deep learning, it's a trial and error, but the best way to choose the best tile size is to at least have most of the object in it. If we're doing something related to an object. For here, I took the tile size is 512. The stride is how much it will move before cutting the other part. Here, it will just take 512, then move, take the other one without intersecting. Okay, after running this tool, before running this tool, you will have this image, the entire satellite image that you have. The tool will cut it into equal-sized pieces. Now to the other tool, which is training the deep learning model. Same thing. You select the exported training data, the folder where you exported your training data, and you select where the model that will be trained will be where will be saved. And if you are fine-tuning some existing model, you can fill this parameter. If you're not, you're training from scratch, you can keep it empty. And I will not go into detail the other stuff, but it's in general like this, the validation, the partition of data. You can select how much validation part of the data you want to make. Like here, I'm saying 10% of the data will be used for validation. Okay, so the model takes these kind of images. Here, what I did, as I said, I had a high resolution image. I only applied some filter to get simulated low resolution image. So this is the high resolution, low resolution, and I give the model each one of the chips. I tell him this is the high resolution, this is the low resolution, and he learns from it. And finally, once finished training the model, we get to the part of inferencing. For inferencing here, the method is used, method used or the tool that is being used is the classified pixel using deep learning. You give it the image, you give it the model, and you run it. Remember always, whenever you're doing inferencing or doing the training, to select the processor type to be a GPU, so it doesn't take a lot of time or it doesn't crash. So once finished, I did all of the, I put all of these this parameter. I click on run, and it will take my low resolution image and enhance some of the feature in it. Okay, that was all. I did want to create a small exercise, but since we have only 1 hour, I will not be able. So if anyone have any question, please do ask.
Mr. Mohamad, you have a question on chat, please. You can read it.
Okay. What do you mean by directly? Since the image is already on ArcGIS, Dr. Nasser, can you unmute the participant? Okay, let me answer, and you can tell me if I did answer exactly. Once you have the image in ArcGIS Pro, all of the tools are already here. The only thing that you need is the deep learning framework that I told you, and additional extension, which is the image analyst to use these tools. So once you have it within the geoprocessing tool, you can go to the toolbox. You have the image analysis tool, you have a deep learning tool set, and all of the tools that you saw are here. These are. So you can directly, let's say I want to export training data. Since the image is already present in ArcGIS Pro, all you have to do is select it and do the workflow that I talked about. And you can also see each step in the documentation and what it does. Does that answer your question? Okay. No, the training for the super resolution one, I didn't find any trained model. So if the living atlas that I showed usually have some trained model. For the super resolution, I did not find. So you must train it from scratch, unless you find somewhere else a trained model, and you can then fine tune. But for this, the one that I showed, you have to train it from scratch. Actually, I didn't have the time, but this is the example that ESRI showed. So this is the image that they gave the model, and this is the output.
You have
Okay.
10 minutes if you want. You have 10 minutes if you want, Mr.
No,
Mohammed.
I didn't have time to run the model.
Ah, okay. No, no.
It's been run before, but I didn't have time
Yes, yes.
to rerun. Okay, other question? No, you cannot directly apply it in Lebanon. Like for this one, I have an example. Just give me a minute. You cannot directly apply it. Even the USA one,
Hmm.
just a second. Even the USA one, like this is the building footprint extraction USA that I showed you earlier. If you apply it to Seattle, let's say, which is a city within the USA, let me just add that. Seattle building potential. Okay, if I directly apply the model on a city within the USA and using the USA model, sometimes it doesn't give a good result. Like here, for example, the problem was the resolution doesn't match. But even sometimes when you run it there, it will not train on the specific feature of the building, it will not run fine. So after a little bit of fine tuning, this is what you get. So instead of this building, just taking a couple of buildings, some fine tuning, smaller data set. I did train it on a small batch of training data, like just this part. I used this building to train the model, and the result was, as you can see on the screen. No, you cannot see the screen. Just a sec. Okay, I was talking about this one. So using the model of the shelf, this is what you get. Let me change the symbology. Okay, I did get the model, run it off the shelf directly. It detects some of the building, but not as much. Whenever we fine tune it, I use this small portion of the building to fine tune the model. Like I only label this part of the image and train the model, and this is the result that I got after fine tuning the model. It was able to detect most of the building. And of course, when you say deep learning, there's not 100%. There's always a margin for error. Other question?
Someone asks, it's a free or
No, of course, ArcGIS Pro is not free. You can get a personal use license, and you can check it online, or you can contact us if you're in Lebanon.
also Ali, I need have a question.
So this needs a very high resolution. Look, whenever you want to know what resolution you need, if you can see the feature with your own eye within the image, let's say you're saying I have a Sentinel-2 image, 10 meter. I want to detect a tree. So the tree, you cannot even see it with your eyes. So like it's logic, you know. For building, like for example, the imagery here, let's see the resolution. It's 1 meter. So 1 meter was enough. If the resolution gets better, the model gets better. Okay. Okay. Another question. Even if you want to try some of the stuff, but of course you must have ArcGIS Pro. There's plenty on the ESRI training. You just Google ESRI training and you can find plenty of courses that you can do. Even you can get a certificate once you finish each one of the courses with the exercise. You can find it here. So the courses can be found here. You can find 3 courses and take it. And for the model, the trained model, you can find them. Just search for Living Atlas. Okay, Living Atlas, arcgis.com, and go to the browse and filter. Since Living Atlas doesn't only have deep learning model, it also have tools, maps, data. Filter for the deep learning packages, and you can find plenty of deep learning packages. Even for the building footprint extraction, you can find multiple ones. Like building footprint extraction USA, India, Australia, Africa, you can find multiple ones depending on the task that you're doing. And the description about or the information about each one of the model can be found in the ArcGIS API for Python in the deep learning section. You can find different 2D, 3D, even natural language processing model and the description about it. These are not ESRI's model, but have been adapted to be used within the platform.
Anyone have a question?
Okay.
Okay.
Okay, so
I will,
if you want to ask another question later, this is my email. You can reach out. Mohamad Chalhoub at ESRI Lebanon.com. I will send it in the chat.
Mr. Mohamad, you have another question.
Yes. Yes. Where do you get that? I don't provide data. I'm telling the tool to use it. But if I find something public, I can send it to Dr. Nasser, and he can give it to you.
No problem. Okay. I want to thank Mr. Mohamad for this amazing and inspiring presentation. And I will repeat my thanks to you. A common LCWE and ESRI certificate will be awarded in this session after completing your assignment after 1 week and which will be online after 1 week. And then after 1 month, we will send these certificates. So you will be awarded 2 certificates, one from LCWE for the 3 previous session and another from ESRI and LCWE from this session. Thank you for all. Assalamu alaikum wa rahmatullahi wa barakatuh.
Okay, thank you everyone. Thank you, Dr. Goodbye.